All right, lesson 8, fission and fusion. So we're going to begin by talking about fission. So fission comes from the word fissure, which means to split. So if you've ever heard people talking about a fissure in the ground, that means the ground split apart. We can also talk about nuclear fission, which is when a larger nucleus splits apart into smaller nuclei. So here's an example of nuclear fission. Let's say we start with uranium-235, and that uranium nucleus splits apart into barium and krypton. That's called fission. Now, by the way, there might also be some neutrons produced here. I'm just not showing them in the diagram. So fission can happen spontaneously, which means it can happen on its own with nothing prompting it, or it can happen with the help of an incoming neutron. That means if a neutron hits the uranium nucleus, that can actually prompt it to split apart into two smaller nuclei. Now, uranium is not the only thing that undergoes fission. There's other nuclei that split apart as well. This is just one example. Next, we'll look at nuclear fusion. So nuclear fusion is when two smaller nuclei combine together to become a single larger nucleus. So for example, let's say we have a nucleus of hydrogen 2, which is also called deuterium, and say we have a nucleus of hydrogen 3, which is called tritium. These can combine together. So this middle part is showing the two individual nuclei coming together. Eventually this is going to form helium-4, and it also forms a neutron. The important part here, though, is that you had two nuclei, 1, 2, merging together to form a new nucleus. And when that happens, that's called fusion. Now, fusion does not happen spontaneously. Fusion actually requires high amounts of input energy to occur. The reason for that is that these nuclei are positively charged, right? So if you look at the hydrogen 2, that has an overall positive charge because it's made up of one positive thing and one neutral thing. And if you look at the hydrogen 3, that's also positively charged overall. To bring two positively charged things close together, you have to input energy because positive things repel due to the electrostatic force. So they don't want to come close together, but you can force them to go close together if you use enough input energy. And the amount of input energy required is quite high, so fusion doesn't really happen here on Earth on its own. Instead, it happens in environments where the temperature and pressure is really high, because the temperature and pressure provides this input energy. And so fusion happens mostly on stars, such as in our sun. Fusion is actually what powers the sun. So, although it may seem that fission and fusion are opposites, they actually both produce energy. So, in both cases, fission and fusion, the measurable mass of the reactants is larger than the mass of the products. And so, what that means is if you compare the mass of the products to the mass of the reactants, some of the mass looks like it has gone missing. Remember that we call that missing mass the mass defect. Now the mass isn't really missing, it's actually just been converted to energy. And that energy is released from the reaction, and you can actually use that energy to generate electricity. That's how a nuclear power plant works. So the energy can become kinetic energy of the products, or it can become heat energy. All right, we're going to compare the released energies. So we know that both fission and fusion release energy. We have to be able to compare which one releases more energy. So if we talk about the energy released per reaction, then that means we're talking about how much energy comes from a single reaction. And something to memorize is that a single fission reaction releases more energy than a single fusion reaction. So here's an example. Let's say we have uranium-236 and it undergoes fission to become barium, krypton, and it also releases 3 neutrons. I've looked this up ahead of time, and this fission reaction releases about 240 mega electron volts of energy. Now let's compare the fusion of hydrogen 2 and hydrogen 3. They're going to fuse together, in this case, to make helium-5, just as an example. And if you look up this reaction, you'll find that it releases about 24 mega electron volts. So fission, a single fission reaction, releases about 10 times the energy of a single fusion reaction. But now, let's suppose that we compare the energy released not per reaction, but per gram of reactants. So in this case, it's actually the opposite. So this time, fusion releases more energy than fission per unit mass of reactants. So just to give an example of what I'm talking about, let's say that I have some marbles. And let's say that each marble represents a uranium nucleus. Okay? If I measure out 1 gram of marbles, I'm only going to have 6 marbles total. Okay? That might not even be true. I just made up these numbers, but I'm just trying to illustrate something here. So because each marble is relatively heavy, 1 gram of marbles is not that many marbles in total, is what I'm trying to say. Now, let's say we have a whole bunch of salt, okay? Let's say that each grain of salt represents a hydrogen nucleus. So since hydrogen is element number 1 on the periodic table, it's a small nucleus. It doesn't weigh very much. Uranium is almost at the very bottom of the periodic table, so it's a bigger nucleus that weighs a lot more. So that's why the marbles are uranium and the salt is hydrogen. Now, if I measure out 1 gram of salt, I'm going to have a lot more than 6 grains of salt, right? 1 gram of salt is probably hundreds of salt grains. So now I want you to imagine, okay, 1 gram of uranium undergoes fission, and 1 gram of hydrogen undergoes fusion. Well, because 1 gram of hydrogen is so many hydrogen atoms, and 1 gram of uranium is not very many uranium atoms, you'll be able to actually do about 234 times more fusion reactions than fission reactions, because the fusion involves the hydrogen and the uranium involves the fission. Don't worry about where that 234 came from. I calculated that earlier, and you don't need to know where I got that from. So, although each fusion reaction produces less energy than each fission reaction, because here there are more fusion reactions, more energy is going to be produced by fusion when you're comparing equal masses. So just make sure to memorize these two things. So first of all, if you're comparing the amount of energy released per reaction, then fission releases more energy. But if you're comparing the energy per unit mass or per gram, then it's the opposite, and the fusion releases more energy. So I just want to show you here if we actually calculate it. So suppose that we have enough uranium to do 6 fission reactions, and suppose that we have equal masses of uranium and hydrogen. If we fuse all of the hydrogen, how will the total energy released by fission compare to the total energy released by fusion? So remember I had said 1 fission reaction releases 240 mega electron volts. So if we're able to do 6 fissions, because we have 6 uranium atoms, then 6 times 240 gives us a total amount released of 1,440 mega electron volts. Now, for fusion, remember we said 1 fusion reaction releases about 24 mega electron volts. And let's say that we have the same amount of mass, so we have 1 gram of hydrogen and 1 gram of uranium. With 1 gram of hydrogen, we can actually do 234 fusions. So if we did 6 fissions, then we're going to be able to do 6 times 234, which is 1,404 fissions. If you take the number of fissions and you multiply it by the energy per fission, here's how much energy you get. It's about 34,000 mega electron volts. So you can see here, in this case, as I was just explaining, the fusion releases more energy. All right, Something else to note is that both fusion and fission produce much, much more energy than any chemical reaction. This is why nuclear power plants are able to produce so much energy. Okay, so just as an example, you don't need to memorize this, and you don't need to memorize the values given in any of the slides. Let's say we have the combustion of methane. So combustion of methane is a chemical reaction. It's not a nuclear reaction. And the amount of energy released by combusting one methane molecule is only about 8 electron volts, just for comparison's sake. So please watch these videos after. I'll put the links up on D2L. All right, now we're going to take a closer look at fission. So we're going to look at the fission of uranium-235. The reason we're going to look at this one is that uranium-235 is what's commonly used to produce nuclear energy in nuclear reactors. So here is kind of what happens, and we're going to write these equations in a second. If you want to make uranium-235 undergo fission, what you do is you bombard it or you hit it with a neutron. This creates uranium-236. Now, uranium-236 is very unstable, and so as soon as the uranium-236 is created, it will break apart into 2 smaller nuclei in an attempt to become stable. And in this case, not always, but in this particular diagram, it breaks down into barium and krypton. Sometimes you get other products that are not barium and krypton, and the question will tell you what the products are. So in a second, we're going to write down some nuclear equations for the steps that are described on the next slide. And when we do this, it's going to be pretty much the same as writing down equations for alpha, beta, and gamma decay, in the sense that we're still going to use conservation of charge, which remember that's the bottom numbers, and conservation of nucleons, which are the top numbers. So, step 1, hit uranium-235 with a fast-moving, high-energy neutron. So, uranium-235 looks like this. So, the 235 comes from the question, the 92 came from the periodic table, and we're combining this uranium with a neutron. Make sure that you have the symbol for a neutron memorized. So it's a lowercase n with a 1 on top and a 0 on the bottom. And it tells us here that this produces uranium-236. So if we look at our top numbers, 235 and 1 makes 236. So conservation of nucleons works there. And then now we have to figure out what this bottom number is, and we'll do that using conservation of charge. So 92 and 0 makes 92. So there we go, that's step 1. Now step 2 says uranium-236 is very unstable, so it spontaneously breaks apart into barium-141 and krypton-92. So I'm just going to write down, there's the symbol for uranium-236 again, okay, and this is breaking apart into barium-141 and krypton-92. So barium's atomic number is 56 and krypton's atomic number is 36. Okay, and it's also telling us here we have some neutrons. So to finish the equation, we have to figure out how many neutrons go right here in this box. So we're going to do conservation of nucleons. So 141 plus 92, that is equal to 233. Okay, and then on the bottom, 56 plus 36, that is equal to 92. So what we can see here is, if we compare 233 and 236, 236 minus 233 is 3. So that means I have 3 neutrons being produced. So I have a neutron, and another neutron, and another neutron. So now on top, I have 233, 234, 235, 236. So now the top numbers are equal on both sides of the arrow. And then on the bottom, I have 56 plus 36 plus nothing because the bottom numbers over here are all zeros. So there's the equation. Now sometimes you might see this written this way instead. Instead of writing out the symbol for neutron 3 times, because that's kind of annoying, sometimes we'll write this with a coefficient of 3, and then the symbol for neutron, same thing. And then it says, note, some of the initial mass is converted to energy during this process. We'll see about that a little bit later. So here's another example. So when uranium undergoes fission, sometimes products other than barium and krypton are formed. So let's say instead of making barium and krypton, uranium-236 breaks down into xenon-140 and strontium-94, and we want to know how many neutrons were produced in this reaction. So I've already written out most of the reaction there. You can pause the video and look at it, just make sure it makes sense to you. And now hopefully you've looked at the reaction. We're going to try to answer the question of how many neutrons were produced. So I've already gone ahead and added up 140 and 94, and I found that that was 234. Over here, this number says 236. So to get from 234 to 236, because that's a difference of 2, that's going to be 2 neutrons. So I'm going to write it this way. Coefficient of 2, and then the symbol for neutrons. So again, this means 2 neutrons. And we should also just make sure that the bottom numbers match. So 54 plus 38, that's 92. This is already 92 here, so that's good. Okay, just a note, if you have something like this, so 3 neutrons, just as an example, when you are doing conservation of charge and conservation of declines, remember to multiply. So 3 times 1 is 3, and 3 times 0 is 0. I just point that out because sometimes I see students adding them together. So in the past I've had students do 3 plus 1 instead of 3 times 1, which is not correct. So just make sure if you're going to use the method where you're writing a coefficient in front of the number of neutrons, to find the totals you have to multiply. Okay, so in a nuclear reactor we have something called chain reaction. So the fission in a nuclear reactor is self-sustaining, which means once you get it started, it keeps going on its own. You can almost think of it as like a set of dominoes, right? If you set up a whole bunch of dominoes and you knock over the first domino, the rest of the dominoes will fall over on their own. Kind of the same idea. So what happens in a fission reactor is that each fission reaction produces 3 neutrons. And then those neutrons collide with new uranium atoms, which produces 3 more neutrons, which can then go collide with more uranium atoms and so on. So if I get the process started here by hitting a uranium atom with 1 neutron, that will create, for example, krypton and barium, but it will also make 3 new neutrons. And each of those neutrons can go and collide with more uranium atoms, which is going to create a whole new set of neutrons right here, which can then go and can collide with more uranium. And so what I'm trying to show here is once you get the process started, as long as there's more uranium available, you'll just keep getting reaction after reaction after reaction. All right, so you may be asked to do a mass defect calculation for fission. And so I'm just going to show you how to do that. It's very similar to the mass defect calculations that we were doing earlier in the unit. So for example, calculate the energy released in mega electron volts for 1 fusion of uranium-235 into krypton-92 and barium-141. Okay, so looking down here where I'm putting the star, there's the nuclear reaction written out. So we know that when uranium undergoes fission, we start by bombarding it with a neutron. those are my reactants. So reactants is whatever's on the left side of the arrow. We know that this is going to make uranium-236, but then uranium-236 doesn't stay for very long because we talked about how it's unstable. So that uranium-236 is going to immediately break down into krypton and barium. And so krypton and barium and 3 neutrons is going to be our products here. How I knew it was 3 neutrons was just by using my conservation rules from earlier. So that's just what I was doing up here. I was saying, okay, 92 and 141, that's 233. Since over here I started with 230, actually I shouldn't really look just at that 235. I have to look at the totals. So 235 and 1 makes 236. 236 minus 233 is 3, so that's where that came from. So what you do if you're doing a mass defect calculation is you calculate the mass of the reactants. So here's me calculating the mass of the reactants. I'm just doing the mass of the uranium-235 plus the mass of 1 neutron, and that gave me 236.526 U. And then I also calculated the mass of the products. And so when I calculated the mass of the products, I just added the mass of krypton to the mass of barium plus the mass of 3 neutrons. And that gave me 235.8661 U. To find the mass defect is just the difference between the mass of the products and the mass of the reactants. So down here in black, I've subtracted those two values, and I actually got a negative number. So I got negative 0.1865 U. That negative just means that mass was lost. So it means that the reactants contained more mass than the products, which is normal. That's exactly what should happen. And to turn mass into energy, what you do is you use Einstein's E equals mc squared formula. But please remember when you use this formula that E needs to be measured in joules. Well, yeah, whenever you use this formula, E is always going to be measured in joules, and delta M, which is the mass defect, always has to be measured in kilograms. So when I was calculating the mass defect, I was working in units of U. Okay, so what I am doing here in the green box is I'm converting from U into kilograms. So to do that, you just multiply by 1.66 times 10 to the negative 27. So the mass defect is 3 times 10 to the negative 28 kilograms. Now I'm leaving the negative out in this step because, again, the negative just tells me that mass was lost, and I just want to get a number for my final answer. I don't really care if that number is positive or negative, so I'm just going to leave the negative out of my work. Oops. Okay, so now we have our energy. So energy is 3 times 10 to the negative 28 kilograms times c squared. So we're just doing m c squared. We can call this delta m if we want to show that it's a mass defect. And then to finish up the question, because the question asked us to do units of mega electron volts, right here I'm converting from joules to electron volts by dividing by 1.6 times 10 to the negative 19 because there's that many joules in every electron volt. Then I divided again to go from electron volts to mega electron volts, and so my final answer after doing both of those divisions was 174 mega electron volts. All right, now we just have to take a bit of a closer look at fusion. So remember I said earlier, fusion requires extremely high pressures and temperatures to get started. And I had said that this was because when you want to fuse atoms, you have to overcome electrostatic repulsion. So remember that if you have a nucleon, so this is a proton or neutron, and you have an approaching nucleon, in this region out here that I'm shading over, they will be repelling one another. Okay, and so if you want to pause the video and just watch this fusion in the sun link and then come back, that would be good. Okay, so last thing that I have to say, remember that fusion requires a lot of input energy. Okay, but remember I said earlier in the notes that fusion releases energy overall. That's because, so if you have a fusion reaction, this is how it will look if you include energy as part of the reaction. So you have your reactants. In order to make the reaction happen, you need to have a high input energy. If you do this successfully and the reaction occurs, then you're going to end up with your products and you will get out an even higher amount of energy than you started with. So it will still release in a net, or still result in a net release of energy. The example that I like to use for this is kind of like saying, if I said to you, okay, if you give me $1 million, I will give you back $5 million. So you give me $1 million and I give you back even more money. So if you could come up with $1 million in the first place, then after the transaction is done, you would have even more money than that. The problem is coming up with $1 million in the first place is difficult to do. So we don't actually do fusion reactions in nuclear reactors because coming up with the amount of energy required to make the fusion happen in the first place is really, really difficult. If we could make it happen, that would be great because we would end up with tons of energy from it. But making it happen in the first place is really, really hard. So we don't actually have fusion reactors, but we do have fission reactors. Okay, here's some examples of fusion reactions. And these are actually the fusion reactions that happen in the sun. You don't need to memorize them, but you do need to be able to look at a reaction and tell whether it's fission or fusion. So just have a look at these, kind of get familiar with them, know that they're fusion reactions, so that if one of these shows up on a unit test and you're asked what type of reaction it is, you can go, oh yeah, well that's fusion, right? And remember the reason it's fusion is we have, for example, here in reaction 3, 2 nuclei merging together into 1 nuclei plus some byproducts. Actually, it's probably easier to see that in reaction 2 than it is in reaction 3. So we have 2 nuclei merging together into a third nucleus, and then this gamma photon here is like